Hello friends. How to implementing a system that manages IoT devices with a combination of pods and fog cloud. Computin explain more. Arman Shariarian IR.
Hello friends, in this training we want to implement IoT device management and IDS protection with neural network and load prediction, energy efficient, load balancing in a micro-IoT environment, and using lens for monitoring can be a complex multi-step process. Let's explain more. Prerequisites: Ubuntu-based environment, since micro-K8s is a native to Ubuntu, and micro-K8s because lightweight Kubernetes for edge devices, and Lens for a Kubernetes IDE, and Python for developing the neural network model, and Docker for containerization, the IDS model, and other microservices. This scenario contains 6 steps. Step 1, set up a micro-IoT. Step 2, deploy IoT device management using fog and cloud pods. Step 3, implement a neural network for IDS protection. Step 4, implement load prediction and energy efficiency. And step 5, monitor the cluster with Lens. Step 6, implement load balancing and scaling policies. Step 1, set up micro-IoTs. For setup micro-IoTs, install micro-IoTs with this command: install micro-IoTs on Ubuntu, and use this command status ready micro-IoTs, and enable required add-ons, for example DNS and dashboard and registry in the micro-IoTs, to set up Kubernetes ecosystems with this command. Micro-IoTs enable add-ons, DNS, dashboard, and registry. Set up namespace. For separating service, create namespaces for IoT management, IDS, and load balancing with these 3 namespace name: IoT, IDS, and load balancing with these 3 commands created. And step 2, deploy IoT device management using fog and cloud pods. This step focuses on deploying and managing IoT device with fog and cloud pods, where fog nodes act as intermediary processing units closer to IoT devices, and cloud nodes handle centralized processing. And for setup IoT namespace and required configuration, first, create separate namespace to logically segregate IoT device managed by fog nodes. Create a namespace for IoT device managed with this command, and configure role-based access control or RBAC optional for security. Define roles and role binding if access control is needed for your IoT namespaces. For example, YAML file for role creation. This script. for YAML role creation file and create role binding with this script. Next, apply this configuration with these two commands. Apply IoT role and IoT role binding file. Deploy IoT fog nodes. Fog nodes are responsible for edge processing closer to IoT devices, so they optimize your low latency and lightweight processing. Define IoT fog node deployment YAML. Create a YAML file, for example IoT fog deployment.yaml, to define your fog node deployment. With this script, and deploy the fog node deployment. Apply the deployment configuration with this command. Apply -f IoT fog deployment.yaml file. Verify the deployment. Check the fog nodes are running successfully with this command. micro-k8s kubectl get nodes get pods and -n IoT -l tier equal fog, and deploy cloud nodes for centralized processing. Cloud nodes manage more intensive centralized task and data aggregation from fog nodes. Define IoT cloud nodes deployment YAML. For this, create another YAML file, for example IoT cloud deployment.yaml file for your cloud node deployment. With this script, and deploy the cloud node deployment, and with apply the cloud node deployment configuration with this command IoT cloud deployment.yaml file. And for verify the cloud node deployment, ensure that the cloud node are up and running with this command. micro-k8s kubectl get pods -n IoT -l tier equal cloud. Set up communication between fog and cloud nodes. To facilitate communication between fog and cloud nodes, create services to expose them to each other. Create a service fog nodes. For create service fog nodes, define a service YAML for the fog nodes to allow communication with cloud nodes. With this script, and apply the fog node service configuration with this command. For apply IoT fog services, and create service for cloud nodes. With define a service YAML for the cloud nodes with this script, and apply the cloud node service configuration with this kubectl apply for micro-k8s with file IoT cloud service.yaml. Verifying the service with check if the services for both fog and cloud nodes are available and their endpoints are correctly set. With this command, get svc -n IoT, and test and monitor the deployment. Verify pod and service connectivity. Execute a quick connectivity test from a fog pod to ensure it can reach a cloud node service. With this command, micro-k8s kubectl execute -it fog pod name and IoT name with IoT cloud service and port 80. Monitor pod status. For use micro KTS commands to monitor pod and service statuses with this micro KTS kubectl get all -n IoT command. And optional configure load balancing for the IoT deployment. Enable a horizontal pod autoscaler if you want to scale fog or cloud nodes based on CPU usage with these 3 commands. First command, enable metric server add-ons, and command 2 for auto scale deployment for IoT fog nodes, and third command, auto scale deployment for IoT cloud nodes with max and min node in IoT device. Step 3, implement a neural network for IDS protection. Prerequisites: Python 3.8 plus for developing the neural network, and PyTorch or TensorFlow for building and training the model, Docker for containerize the model, and micro-KTS for deploying the IDS model and data, a labeled dataset, for example NSL KDD or UNSW NB15 for training and testing. Design and train the neural network model. Set up the Python environment. For create a new Python virtual environment with this command, python 3-m IDSenv, and with this command source locate, and with this command install torch and pandas and scikit-learn. Prepare the IDS dataset. Download the dataset, clean it, and split to training and test sets. Import with this script, and for define the neural network architecture. This simple neural network takes a features vector for network traffic data as inputs and classifies it as normal or an intrusion. For this script, train the model on the training set with this command, and not command, this training this model, this script, copy and paste file for training set model, and containerize the IDS model. Create a Python script file to serve the model. Save this script as IDS service.py. It loads the trained model and set up a REST API to classify network traffic data with this script, and create a Docker file to containerize the model and the REST API service before run a script. This you must create required file, and with this 3 parameter, and build and push the Docker image. Next, for build the Docker image and push it to container registry if needed. These 2 command, and first command for build Docker, and second command for push your Docker, and deploy the IDS model on micro-K8s. Define the IDS for deployment YAML with create a YAML file, for example IDS deployment.yaml, to deploy the IDS model as a service, IDS model as a service in the IDS namespace with this script, and create a service for the IDS model. Define a Kubernetes service to expose the IDS model deployment internally or externally. With this script, and next apply the deployment and service. Deploy the IDS model to the micro-K8s cluster. With these two commands, apply IDS deployment and IDS service file, and verify deployment. Ensure that the IDS deployment and service are running successfully. With these two commands, get pods and get SVC for IDS node, and test the IDS model. With access the IDS model API, you can test the model by sending post requests to the predict endpoint. With this command, monitor tag, with monitor the logs of the IDS container to ensure it's working correctly. With this command, kubectl log for IDS. Step 4, implement load prediction and energy efficiency. Prerequisites for these: Python for developing the load prediction model, scikit-learn or TensorFlow for building the predictive model, and Docker to containerize the model, and micro-K8s for deploying the model and setting up resource manager. Design and train the load prediction model with set up the Python environment, and create the new Python virtual environment and install necessary libraries with 3 commands. And prepare the data for load prediction. Use the dataset with load and usage data to train the prediction model, and data can be gathered from historical CPU, memory usage, or any specific metrics related to your workflow. With this script, and define and train the prediction model. With here we use a simple linear regression model, which can be replaced with more complex architecture if needed. With this script, and containerize the prediction model with create a Python script to serve the model. Save this as load predict service.py. It loads the trained model and provide an API for load prediction. With this script, and create a Docker file to containerize the prediction model service. With this script, after before run this Docker file, you can make a requirements text with these 3 parameter, and next run Docker file. Build and push the Docker image. Build the Docker image and push it into a registry if required. With these 2 commands, build and push. Deploy the prediction model on microK8s. Define the deployment YAML for load prediction. Create a YAML file, for example, load predict deployment YAML to deploy the model in the load predict namespace with this script, and create a service for the load prediction model. Define a Kubernetes service to expose the predict service with this script, and apply the deployment and service with deploy the prediction service in microK8s with these two commands for apply load predict deployment and load predict service file, and verify the deployment. Ensure the prediction model service is running correctly with these two commands: microK8s kubectl get nodes, get pods, and get svc. Implement energy efficiency and load balancing. Enable metric server. For metric server, provides essential resource usage data to support the horizontal pods autoscaler or HPA. With this command, microK8s enable metrics service first and define HPA for load prediction service, and use HPA to scale the service based on CPU usage. Optimize energy used by running only a necessary number of replicas. With this script, and next apply the HPA configuration with this command: kubectl apply load predict HPA file, and configure node resource limits and power policies. Optional, use cluster autoscaler or node resource limits to reduce energy consumption by efficiently managing node and pod resource allocations. Test and monitor. Check the HPA in action by simulating load, which should automatically increase the number of replicas. Use kubectl top command to monitor resource usage with this first command, and with this get HPA second command. And step 5, monitor the cluster with lens prerequisites microK8s, and set up the with workloads, IoT, IDS, and load prediction deployment, and metrics server enable, and use lens tools for install on your local machine. With this URL, you can go this URL and download lens. Configure microK8s for lens. Enable metrics server if not already enable metrics server in microK8s. Provides necessary cluster resource metrics, for example CPU, memory, and other, which lens relies on for real-time monitoring. With this command, enable add-ons metric server, and install RBAC add-ons if needed. If your microK8s configure requires role-based access control for lens to retrieve metrics, enable RBAC. With this command, enable RBAC add-ons, and set up access permissions if using RBAC, and create a cluster role binding to grant necessary permission with this script, and apply the configuration file with this command for apply lens access file. Access microK8s from lens with generate kube config for microcaches with lens require access to the kubeconfig file. For your microcaches cluster, use the following command to generate the kubeconfig file with microcaches config, and this command outputs the kubeconfig for the cluster to your default Kubernetes config file. Locate this location file, make sure the user can read access. Test connection, for test connection, verify that you can access the microKAS cluster using kubectl command from the local machine. With this command, get nodes and connect microKAS to lens, launch lens, with open the lens application on your local machine, with add a user cluster, go to the file menu and select add cluster in lens app, select the config file where your microKAS configuration is located. Lens will automatically detect the cluster defined in the file, configure cluster setting in lens, and after adding the cluster, select it from the lens home screen. Under setting, configure the following metric stacks with enable metric collection if it isn't auto detected, and refresh interval, adjust the refresh interval for metrics to get real-time data updates, and next click apply and save this setting. Monitor cluster metrics. For monitor cluster metrics, view cluster overview. In lens, select your microKAS cluster from the left sidebar. The overview tab will display CPU, memory usage, and overall cluster health. You can also see resource utilization at a node and namespace level. Monitor namespace. With navigate to the workloads tab to view deployments, paths, and replicas in each namespace. For example, IoT namespace and IDSS namespace, and load prediction namespace, and other namespace. In setting, configure alerts for events like high CPU or memory usage, or when a path status changes. Enable notification to receive alerts directly within lens for prompt action. For customized dashboard for IoT, IDS, and load prediction monitoring, create a custom view in lens. Allow you to filter by namespace or labels to customize view, and you can use IoT monitoring and IDS monitoring and load prediction monitoring, and you can go to paths in each namespace, for example IoT, IDS, and load prediction, and select logs to see real-time logs, and under each namespace workload, select individual paths to view a specific CPU or memory usage, and monitor key metrics like CPU and memory consumption for each path to ensure efficient usage, and identify potentially bottleneck or resource hogging service. Set up lens metric graphs for long-term monitoring. In the cluster setting of lens, use the metrics tab to view, analyze historical data for better energy and resource planning. Adjust the time window to see trend over day or week for resource optimization and planning. Step 6. Implement load balancing and scaling policies. Implement load balancing for services used with Kubernetes uses services to expose application running on pods and load balance traffic across multiple pods or to ensure high availability or HA. For create a service for load balancing, we'll create a load balancer or cluster IP type service for each deployment. For example, IoT, IDS, and load prediction to evenly distributed traffic across pods with this script. For apply this service with this command, apply load predict service and verify the load balancer with confirm that the service is distribution traffic across pods as expected. You can use kubectl describe service command to check endpoints and verify pods IPs. Enable ingress for external access optional. If you need external access, enable the ingress add-ons in microktos with this command. Enable ingress add-ons. Then define an ingress resource to manage external traffic with this script. And next, apply ingress resource with this command for apply load predicts ingress file, and configure horizontal path auto-scaling or HPA. Horizontal path auto-scaling automatically scale the number of paths in the deployment based on CPU and usage memory or custom metrics. Enable metric server. With enable metric server, metrics server should already be enabled from previous step. If not, enable it with this command. Enable metric server. Define the HPA policy with create a HPA configuration for each deployment. Will scale the load prediction service based on CPU utilization with this script. And next, apply HPA configuration with apply file load predict HPA with this command, and verify the HPA. Use the following command to verify that HPA working expected. Get HPA load predict. You should see that the number of replicas adjust automatically based on CPU usage, and implement vertical path auto-scaling or VPA. Vertical path auto-scaling VPA adjusts CPU and memory requests or limits for each path instead of scaling the number of replicas. This is particularly useful for optimizing resource allocation for each path. Install vertical path autoscaler with microktos doesn't natively support VPA out of the box. So we need to deploy the VPA operator manually with this autoscaler from GitHub download, and with this command apply deployment file VPA deployment VPA RBAC and V1 VPA V1 CRDN. Define the VPA policy. For define the VPA policy, configure VPA for the IoT deployment to automatically adjust CPU and memory allocations based on observed utilization with this script and apply the VPA configuration with this command. Apply IoT VPA.yaml file. For verify VPA is running, use this kubectl describe VPA IoT describe and fine tune scaling policies for energy efficiency, set path resource requests and limits, define resource requests and limits for each deployment to control CPU and memory allocation more precisely with this script, and configure path affinity and anti-affinity. Use path affinity and anti-affinity to improve nodes utilization and energy efficiency by collocating or separating specific nodes with this script, and set node resource quotas. Configure quotas on node resource usage to prevent paths from consuming excess resource, especially in resource constrained environment with this script, and apply quota configuration with this command micro k8s and apply node resource quota file, and finally monitor and adjusting policy. Observe scaling behaviors with monitor the HPA and VPA performance in length or by using kubectl top path and kubectl describe HPA or VPA command. Adjust policies based on observed behaviors. Analyze metrics and fine-tune using lens or another monitoring tool. Check CPU and memory usage and path replication rates. Adjust minimum replicas and maximum replicas and resource limiters to align with actual workload requirements. Test scaling under load to ensure policies are effective. Simulate load on each deployment. You can use load testing tool like WRK or Locust to generate HTTP traffic. Implement regular review. Make regular review of resource utilization metrics and adjust resource requests or limits, HPA and VPA setting as needed for optimized scaling and energy efficiency.